I think we'll let folks continue to trickle in, but hello, everyone. I hope you've had a wonderful third day. Our next speaker is Abhishek. He is a senior principal machine learning and AI architect at Schneider. I had to read that one, and an instructor at Northeastern. If you want to learn everything about machine learning algorithms for IoT systems, that's the title of this course. You'll have to become a Northeastern student. But today we are going to learn about using foundation models for anomaly detection. That is, take it away.
Okay. Hi, everyone. Thank you for the introduction, and thank you, PyData, for having me and organizing this really nice event. Uh, I'll be talking about applying foundational large models for time series for the anomaly detection problem. Um, this is a little bit about me. As Adam mentioned, I work for Schneider Electric. It is a French company and a global leader in energy management and industrial automation based in the greater Boston area. I also teach some of these topics on classification, anomaly detection, and forecasting of time series at this course at Northeastern. I primarily work with IoT data, which is in the form of time series. And so all these problems that I just mentioned is something that is very interesting to me. And these are some other places that I have been associated with in the past. Connect with me on LinkedIn, and we can chat about everything time series, right? Um, cool. So with that, my agenda is as follows. I'll start with a gentle introduction and then lay out this promise of zero-shot novelty detection for time series data. We'll go over a couple of models, TimeGPT and MOMENT. MOMENT is an open source foundational model. Look at how they perform on a couple of toy data sets, and then conclude with a summary and recommendations to go forward. Right? Um, Time series. So we often understand time series as a collection of ordered measurements, right? These measurements can be multidimensional in nature, and they often tend to have some repeated patterns in them, right? So consider this univariate ECG signal. This has this repeating train of pulses, which is the repeating pattern in the time series, right? And so any subsequence that deviates from this repeated pattern is called an anomaly, and it's often very interesting. So in the case of an ECG, you could have a slight delay in one of these pulses, which becomes a subsequence anomaly, or it could be a point value, which is either too high or too low. It's often referred to as a point anomaly. When there are multiple dimensions, often the invariant happens to be the correlation between some of these features. The relationship between the various dimensions is often preserved, and if there is a breakdown at any point, these are called correlation anomalies, and they are very interesting in various domains. There is a growing market for time series anomaly detection, as shown in this market intelligence report, and correspondingly, there is a pretty rich body of literature on time series anomaly detection. This is just a snapshot of various techniques that have been applied to this problem, taken from a survey published in VLDB a few years ago. But as we'll see, the community of foundational models has generally not looked at time series so much, and they're starting to wake up to this opportunity, and this talk is all about that. Um, that was TSAD in general. I'm specifically interested in a variant of anomaly detection in this talk known as novelty detection. Right? So in novelty detection, the machine learning model does not have access to anomalies during training, right? In my world of industrial IoT, this can happen because you have just rolled out a new family of assets, so we haven't had any anomalies to observe yet. Or it could be the case that we just haven't kept good track record of observed anomalies in the past, which happens quite often, right? So in novelty detection, the machine learning model just learns from nominal data. So in that sense, it is a one-class classifier that we have all studied, right? And so the model essentially learns to recognize what nominal normal patterns are, and therefore can recognize any deviations from nominal behavior. And that's the definition of novelty detection, right? Identifying new patterns that we had not seen during training. How can we use this? At least in the IoT world, it enables what is known as predictive maintenance. So if an asset was working fine till now and you start observing deviations from the normal, the model picks up some of these deviations. Those deviations could be an early indicator of a fault developing, right? So instead of waiting to react when the asset actually breaks down, you can use novelty detection to detect subtle deviations early on, do service interventions, and make sure the asset is available to the maximum extent. Right? So at least predictive maintenance is a big use case in the industrial IoT, and novelty detection is often how it is solved in the IoT world. The inference can happen in a batch-wise fashion, or it can happen in the streaming fashion, right? So once you have the novelty detection model ready, you start streaming in data. As new data comes in, you detect any deviations that could be there in there. And if there are no deviations, the anomaly detection model will say everything's fine, right? So it's all about detecting novel patterns. How has this problem been traditionally solved in the past, right? Conventionally, what we have done is create a dedicated model for every use case, right? So for every use case, we do our usual workflow of collecting nominal data from the asset of interest. It could be the physics that you're interested in. So this is IoT data in the form of time series. It could be some kind of vibration measurement, some electrical measurements if you're interested in electrical equipment. And then we do the usual exploratory data analysis, feature engineering, and then go ahead and train this novelty detection model for our data, right? The novelty detection model, as I just mentioned, learns what the normal looks like, and it's able to essentially say the new data point, the previously unseen data point that you have given me is either normal or not normal. So it's a one-class classifier. And once trained, we can start inferring on this data the kind of data that we just trained on. And once we get the features, we feed it to the model, and the model usually tells us this new test point is similar to what I had seen during training, and it quantifies the similarity using an anomaly score. And usually the interpretation is if the score is low, then the data point that you just showed me is similar to what I had seen and therefore is nominal. Or if it is very far, if the anomaly score is very high, it often means that this is a new data point that I have not seen before and therefore could be indicative of an anomaly, right? The important point to note is conventionally this has been done in a bespoke fashion. In the sense, for every use case, for every kind of asset, you train these models. So here's an instantiation of how this is done for autoencoder neural networks, right? So autoencoder neural networks contain two parts, the encoder and the decoder. Typically the way they work is you provide them some time series data, and the encoder learns to reduce the data into some lower dimensional representation. The decoder network takes that lower dimension embedding and then reconstructs the original data back, right? And then we can compare this reconstructed data from the original data to see how well the reconstruction occurred, right? So the idea is the autoencoder network can reconstruct the data well if and only if the data was nominal, because you show the autoencoder all kinds of nominal patterns, so it only learns to reconstruct nominal data. And once the encoder and decoder are trained, you send it for inference, and the inference works as follows. You take the new previously unseen data point, pass it through the encoder, get the lower representation embedding, low dimensional embedding, and then try to reconstruct the data from that, and compare the reconstruction error to what you saw during training, right? If the reconstruction error is low, then probably what you saw is similar to the training data and therefore is nominal. But if the autoencoder network fails to reconstruct this data point very well, it means that this could be a potentially new data point that it had not seen during training, right? The autoencoder is trained on the specific data for the use case, and it can reconstruct the data well if and only if it is nominal. right? Because it was shown only nominal data during training. This is just a way to instantiate this workflow on the left for autoencoder networks. But of course, the paradigm is changing, right? The next step is proposed to be these time series foundational models, right? Um, how do time series foundational models work? Now, just like the LLM community, we don't have to train our own models on our data, right? So here is a TSFM. You throw the data at it, and it will automatically generate an anomaly score for you, right? So there is no bespoke models anymore. You can use one of these TSFMs to start doing anomaly detection from get-go, right? From day zero, you can provide it with some data. If the data looks normal, the TSFM will say so, and if there are any anomalies that it has observed in the recent past, it'll throw a flag up saying that I think something's wrong. So no training required. And of course, if you want better performance, you can fine tune one of these TSFMs for your domain, your data set that you are playing with. Right? That will give you better performance. So how do these TSFMs work? Obviously pre-training, right? That's the main ingredient. So these TSFMs train on massive amounts of time series data. And by doing so, they essentially learn the core structures of time series. Right? So time series are often characterized by trend and seasonality. And so by looking at all these massive number of data sets from diverse domains, they are able to pick up on all these important structures. And they can also exist at different scales, right? This multi-scale nature is also very important because then you want to be able to apply this to any domain, to an ECG data set, which occurs in milliseconds time scale or even lesser, to power demand data set, which probably works in the order of hours, right? So massive data sets used for pre-training to learn different structures enables these TSFMs to be foundational in nature, right? So the same model can be used for different types of time series tasks. So you can do forecasting with it, you can do anomaly detection with it, and of course you can do any kind of imputation or filling in missing data kind of tasks also with it. Right? With the same model, you can do all these three different tasks, and that makes it foundational, right? And finally, you can always fine tune this model to your domain. So if you're playing with the energy management data, you can use it to do these tasks better for your data. And if you're working with wearables, then you can use your accelerometer and PPG sensor data to fine tune these models. So the whole idea is if you can complete sentences using an LLM, you can forecast the next value of a time series. Right? And if you can forecast the next value of the time series, you can do anomaly detection, so on and so forth. Um, Several players have proposed TSFMs, and Google, Salesforce, Amazon have all come up with their own models. Today we'll be focusing on a couple of them, Nextla's TimeGPT and Carnegie Mellon University's MOMENT, which is open source, and look at how these work. Right? So the whole idea is we're trying to move away from bespoke models to foundational models, which can work in a zero-shot sense, or you with minimal fine-tuning can work very well. So you can get going pretty quickly. Right? That's the whole idea of disruption in the time series foundational model. You can get going pretty quickly for these foundational tasks of forecasting, anomaly detection, and denoising. So let's look at TimeGPT and MOMENT next. So TimeGPT is from Nextla. So here is a QR code if you want to scan it to get to the model, you can do that. So Nextla, if people that work in the time series forecasting world know that they have some very interesting libraries for forecasting. They have now come up with a proprietary transformer-based model. And so this model is very similar to what the LLM community uses. The only thing is now they have trained it on a massive data set. They claim to be training it on about 100 billion data points. They don't tell us how many parameters are there in the model today, right? And these data sets come from very diverse domains like finance and electricity all the way to tourism, right? And the goal is to be able to forecast the time series. Right? Forecasting is the foundational task that they excel at. So we can provide the time series of interest. So you can just take any time series you want. If you have some exogenous variables, you can use them as well. Provide it to the API given by Nextla, and it will tell you what the next values are. Right? Um, we can use TimeGPT for anomaly detection. They have native support. They provide some API specifically for anomaly detection. And the idea of using TimeGPT for novelty detection is as follows. You just take your data and start creating forecasts with it. As the data streams through, at every point, when you generate the forecast, you also create a confidence interval around it. Right? So essentially, if your forecasting is so good that when you observe a data point, if it disagrees with your forecast, then it's most likely an anomaly. Right? And remember, you're not training a forecasting model here. That comes with the TSFM. So you forecast the data point. If the observation disagrees with your forecast too much, then most likely it's an anomaly, right? So how do we characterize too much difference? It's done using confidence intervals. And this is an example that we'll look later in the slide. So here, essentially the black curve is the observed data point. The pink curve represents the forecasts generated by TimeGPT, right? And this shaded region represents the confidence interval. So a 99.9% confidence interval essentially ensures that the true average value will lie within this region 99.9% of the time, right? This is a pretty strong guarantee, and therefore the confidence interval is wide, right? If you reduce this number, then say for 50%, then you only need to ensure that the true value is within this region 50% of the time. Therefore, the confidence interval shrinks, right? So the consequence of reducing this number is that you are more aggressive, you're more trigger happy when it comes to anomaly detection, because it's easy to be outside that narrow range, and therefore there is a higher chance of false positives, and your precision can go down. But of course, if you are very conservative and use a very strong guarantee like a 99.9% confidence interval, you may take a hit on your recall rates. And so that's how it works. So at every point, you forecast the next few values. Then you observe what the new data came in. If the observation is very different from your forecast, then it's suspect. Right? Going one level deeper, so the whole idea of using TimeGPT for anomaly detection entails, let me just show you um, the function signature, right? So this is the data frame that we provide with the pandas data frame that you can provide. You need to tell explicitly what the time scale is of your data. H and step size pertain to the forecast that is being made. These are overlapping windows of 8 time steps that overlap by a size of 6. And then level is the confidence interval threshold, right? This essentially ensures that the true value will lie within your confidence interval 99% of the time. And detection size is the tail end of the data that you give that you are interested in to find anomalies in, right? So going back to this figure, so this is your entire data frame. You're interested to find anomalies in the last few data points, and of course, this is the window that's going to slide through your data. And you're interested in finding anomalies in this tail end, right? Of course, because there could be anomalies present here, we do not use this window to produce the confidence interval. This window is where you are comparing with the confidence interval that was produced based on all this previous data. Right? So this is a function signature, and a little bit about how TimeGPT works. We are going to look at how it works on concrete data just a bit. Next, I want to introduce MOMENT, which is the open source foundational model from Carnegie Mellon University. And the Auton Lab folks have proposed it, and the lead developer is Mononito Goswami. Here is the QR code. If you're interested, that will take you to the GitHub page of this model. To start with, they created their own data set, which is also public. It's an interesting data set called the Time Series Pile. It has about 13 million different time series spanning about 1.13 billion timestamps. Um, in a modern sense, it's a very small data set. It fits on your laptop, right? It's 20 gigs. But they claim to have covered, again, diverse domains that they can use to pick up on all these fundamental structures that I talked about. And they train the moment model based on this data set. So how does that model look? So the idea there is they have done some interesting things. Firstly, they do not explicitly handle multiple features. They handle one feature at a time. So if you have a multivariate time series data set, it essentially works feature by feature. And we don't have to specify the frequency, the time scale of our data set explicitly again. And remember, these data sets can have very different amplitudes. Some data time series can be of a smaller amplitude, or other time series could be of much larger amplitude. And that's where this technique called reversible instance normalization has become popular in the time series community as a normalization step. They use that in their model. And moreover, they internally use window sizes that are of fixed length of 512. Right? So in my experience, window size selection is a tough problem for time series. There have been papers written just on this. Essentially, how do you automatically find the characteristic length of a time series that you study at a time, that you analyze at a time, is the problem of window size selection. Interestingly, the authors made a selection of 5112, and they always use it no matter which data set that you are using. Internally, the transformer that they use is a simple, again, vanilla transformer from the LLM community. And finally, they use this so-called lightweight prediction head, which come in different flavors. So if you're interested in reconstruction, they give you a reconstruction head. If you are interested in forecasting, they give you a forecasting head. And a way to fine tune is what is known as linear probing. You can just fine tune the final layer, this particular layer, to your task, right, instead of training the entire weights. That's the idea of modularizing it and giving you this prediction head. And so we'll be specifically interested in the reconstruction head in just a sec, right? And yeah, this model is available from Hugging Face, and you can start using it from get-go. How does Moment work? It works essentially as an autoencoder, right? The one that we just looked at earlier in the presentation. So here is the reconstruction specific head that you're requesting, and you can get your model going like this. And what the model essentially, what we are going to do with this model is to take the time series that we are playing with, chop it up into windows. Contiguous windows could work, but if you have overlaps, you of course get more robust performance. So here we're just going to window this data using tumbling continuous windows, and then use the model to create the low dimensional embedding, right? So we're going to encode our windows using this model that we get from Moment, and we're going to reconstruct it. So they have functions for encoding and reconstructing. And we're going to compare the reconstructed windows from Moment with the original windows, and look at the reconstruction errors. So the reconstruction errors look something like this, right? And I'm just going to measure how far the reconstruction is from the original. And this signal may be noisy, as it is shown here. So instead of using like the max reconstruction error that I saw during training, I can use slightly more robust statistics of it, essentially to characterize what normal data looks like. All this is done for normal data initially, right? So I'm going to pass a bunch of nominal data. Because this is novelty detection, we have access to normal data. I can study the reconstruction errors of Moment for normal data, right? That's step one. And then during inference, I can take the data points that I get and do the same process and see how well does the test data reconstruction error compare to what I saw during training, right? If I know what is the typical error Moment makes on normal data, And for a new data that I want to infer on, if it works very badly, then maybe it's an anomaly. Right? So treat it as if someone has given the autoencoder for you, is how MOMENT works for anomaly detection. Right? So TimeGPT, which is mainly forecasting based, MOMENT, which is mainly reconstruction based, can be used for novelty detection. MOMENT is open source, and TimeGPT is proprietary. So having seen these two, let's look at how they work on some actual data. But before that, I actually want to digress a little bit. Because I think before we can see how they work on time series data, we need to clarify how do you measure performance. And so when it comes to time series anomaly detection, precision and recall has been refined a little bit. Right? So when we have our classical tabular data, this could be some bank transactions or credit card transactions that we are looking at. You could train a model on this, and essentially when a new data point comes in, the model predicts whether this transaction looks weird or not, right? And so for tabular data, these predictions are unambiguous, right? You unambiguously know whether the data point is, whether the prediction was correct or not, right? So either your prediction agrees with the ground truth or it does not agree with the ground truth. For time series, this is not the case, right? For time series, what could happen is your anomaly may be spanning from 10 o'clock to 10:30 in the morning, but your model predicts the anomalies began at 10:15 and went on till 10:35, right? So this partial overlap between the ground truth and the prediction makes it difficult to use the classical notion of precision and recall, right? You get weird behavior from this. And so people thought about this, what to do, and back in 2018, the folks at MIT and Intel came up with this paper where they refined these notions to account for partial overlap that occurs when you're playing with time series data, right? And so how do we exactly define precision and recall when the prediction cannot be unambiguously called a true positive or a false positive, but there is partial overlap? So here's a QR code that will take you to the open source GitHub repo for this package, which again can be installed and used as follows, right? So you essentially the package is called PRTS. You can go ahead and install it, and instead of using the classic sklearn based precision score and recall score, we can measure what is known as TS precision and TS recall, right? So what do these notions do? They are essentially telling us that they're quantifying the following aspects, right? So firstly, you want to reward the algorithm if it predicted and caught at least some of your anomaly. As long as even a sample of your anomaly ground truth was predicted by the algorithm, you want to reward it. That's known as the existence, right? As long as it's able to detect the existence of the anomaly correctly, you reward the algorithm. So in this case, the algorithm gets the existence reward, otherwise it will not, right? So if your prediction completely misses the real anomaly, you don't give it any existence reward, right? And so the rest of them can actually be customized. There are parameters corresponding to size, position, and cardinality. And for your application, you can tune these parameters and use the functions for measuring precision and recall, right? So what is size? Again, going back to the concept of if you had the real anomaly going all the way during in this span of time, and the algorithm picked up about 60% of it, you want to treat it differently from a prediction that had only 10% overlap with your ground truth. So size parameter allows you to penalize an algorithm for this aspect, right? Um, Moving on, we may be interested in the start of the anomaly more than the end of the anomaly, right? So if you're interested in some kind of a defense application, something really bad happened, and you may be interested in starting the initial part of the anomaly more than the tail end. So the exact position, which part of the anomaly did you catch, is an important aspect. So the position parameter allows you to tune that. And finally, cardinality, right? So if you made a very fragmented prediction, you want to penalize the algorithm. So for example, if you had a variable and you started playing a sport and you did that from 10 o'clock to 11 o'clock, but instead of detecting one big activity, it detected three sub-activities, you will not be happy, right? And so cardinality penalizes the algorithm if it's predicting the anomaly in a fragmented fashion. So in this package, there are all these different knobs that you can tune to make it customized and measure the performance of anomaly detection that suits your application, right? So please take a look at PRTS. I think it's an important one for the TSAD community. Going on, let's quickly go through a few examples of how TimeGPT and MOMENT worked. So we're going to look at the UCR data set for time series. Again, like it's a very interesting and an important data set. There's a very interesting backstory from Professor Eamon Keogh at UC Riverside. So look at that YouTube video link from that QR code for this backstory and why this data set is important for the time series community. So this is some air temperature data set, which essentially measures periodic variations, and the anomaly is right here, right? So there is some periodic pattern, and you see some different pattern on these days, which is considered to be an anomaly. And this is what TimeGPT provides us, right? So the red dots are the anomalies that are predicted, but the actual anomaly is somewhere here, right? And the way this data set typically works is the first 4,000 data points are considered normal, and the rest of the data is testing data, and the anomaly lies between the indices 6006 to 6054, right? So this is usually considered a good benchmark for anomaly detection, and when we looked at TimeGPT, it did produce quite a bit of false positives. But I think if we look at it from a high level, on normal data, the forecasts look pretty good, and the confidence intervals are also pretty tight and decent. And so whenever there is an anomaly, this is the example that I showed you earlier in the presentation, the observation, the anomalous observation does lie outside the confidence interval, as we expect it to do, right? And when we use the time series precision and recall, we get we get pretty decent recall, and we have quite a few false positives. ECG data, right, is difficult to forecast for this model. And as we can see, it produces quite a few number of false positives. The precision is pretty low, right? And we can see why that is happening, right? Because we are not forecasting anything. And of course, the goal of this is not to say that TimeGPT is not good. The goal is no free lunch, right? So you need to tune the parameters. You need to make it work for your use case. Uh, Zero shot may not be zero. You still need to give it a few shots, and then it will work, right? And Moment, on the other hand, is very interesting. So this is the same data set, and this is the anomaly that we talked about. These are the reconstruction errors of the autoencoder based approach from Moment that I talked about. And what we do is we look at the 98th percentile of the reconstruction error and multiply it by 3 times, right? So if I see a data point that I'm able to reconstruct so poorly that the error is 3 times the 98th percentile that I saw on nominal data, I think that's reasonable to say that it's anomalous. Right? That's the approach that we are taking. And here it's really important to take to determine the size of those windows. Internally, Moment uses fixed size windows, but you can always have different sizes that you use. And so window size and threshold tuning are important parameters. And this one, when tested, there is a huge spike on around the anomaly, and so the reconstruction for this segment was really bad, which we expect, and everywhere else the reconstruction was reasonably okay. There are some few spikes which almost became anomalous, and when we look a bit deeper, we think maybe they were actually anomalies, right? That we are picking, these are not labeled properly. But this was just an interesting artifact that I noticed. Um, Finally, ECG dataset, again, I think the reconstruction errors are pretty bad around the spikes. Consequently, we get massive thresholds with this data. But still, it manages to do better, at least in a zero-shot sense, right? When you quickly pass in the data, this is the reconstruction errors. These are the reconstruction errors on test data. And definitely there is a spike around the actual anomaly, but we also see some spikes other than the anomaly of interest. And these are false positives, and that's what drives down the precision of the algorithm, right? And I think this is mainly because those spikes on an ECG signal were harder to reconstruct as they were harder to forecast for TimeGPT. With that, let me just stop with this summary. Right, most important points is to note that TimeGPT is a forecasting-based novelty detection approach. Moment is a reconstruction error-based anomaly detection approach, right? They both use transformer networks. This is completely open source. Even the data set that they trained on is available to do other stuff. Important knobs for Moment are the window size and the threshold that you do. And on the TimeGPT side, there are a few knobs that you can use to change. And by the way, both these models allow you to fine tune them, right? I have not used any fine tuning. These are really zero shot in that sense. Um, and yeah, I mean, there's a tendency when we look at time series to pre-process them using some kind of sklearn scalars. You don't need to do that with these models, right? You can just throw them, add the models, and they'll do something for you, right? In fact, Moment explicitly tells you not to pre-process because they use that Rebin normalization technique internally. Cool. So this is a summary, and I'll open up for questions. Yeah.
Oh, thank you. So some of these anomalies are rare events, right? They don't happen every day or every week or every month. So how do you approach that type of thing when you have anomaly detection of rare events?
So from a zero-shot sense, right, like if you're using foundational models, they don't know what domain you're coming from, what anomalies they are.
I know, but you're a practitioner, so I'm just saying,
Right.
like, I understand that this methodology
Right.
might not know, right? So like, I need to apply like time
Yeah, yeah.
series in the real
That's what I'm
world.
coming to, right? So depending on if you have some prior knowledge, domain knowledge of what happens if there are more anomalies on a certain day than others under certain conditions, you have these knobs that you can tune, right? You can bring down the error thresholds that will make your algorithm more trigger happy if you're expecting more anomalies on certain time periods, or you can make it more conservative, right? So there are these, it's not completely zero shot. You still have to tune these knobs based on your specific data set.
Sure, but if you have so few examples, it's hard to turn those knobs, right?
Right, but that's why you have, that's the whole point of novelty detection, right? Novelty detection does not need any anomalies. So the whole idea is, can you just use your normal data to understand what your typical forecast errors are, typical reconstruction errors are, right? So novelty detection does not require any labeled anomalies. This is precisely why we use this approach, where the model just learns to detect what is normal. And I'm hoping that is available, right? Normal data should be available.
I love these questions. We have time for one or two more
Yeah.
questions, and then I'm sure in the hallway, Abhishek will be able to
Yeah,
speak
yeah.
more. But here's
Thank you. Do you think it's worth looking at these approaches for non-periodic, non-stationary data, like sequences? I feel like the zero shot obviously wouldn't work, but is that type of data represented in the training data for something like Moment so that you could use the transformer outputs for dealing with that type of data?
Correct, right? So specifically that Rebin normalization works with non-stationary data, right? And it's not just Moment that came up with, so that kind of normalization technique is very popular out there, specifically for non-stationary aspects.
So great talk. I have quick questions that, in your experience, what's a typical failure mode that those two actually come up with? Is that like, for example, like the outlier masking or like a sparse sampling? Another thing is that this provide a nominal score, but do you have something like can enhance the explainability for this? Like a kind of, yeah, whether you can do that. Thank you.
Yeah.
For time series data.
Explainability part, at least from Moment, is relatively easy because you need to use it on a feature by feature basis. Right? So you know exactly which feature is causing it, and that feature will be associated with some measurement that you can go with. TimeGPT is all about forecasting, right? So um, I I need to check if they have some kind of feature importances that they give, right, which can be used or SHAP-based approaches that are possible. But when it comes to error modes, I think it'll primarily come, like you can understand if your model is working well or not just based on the forecasting errors or the reconstruction, right? So it allows you to at least figure out very quickly whether it's working or not, right? And then you can understand there are these knobs that are available to understand. But I'm not aware of a systematic analysis of various failure modes for these models. Um,
When
but
someone
at least for a
invents
moment, it can be done.
when someone invents SHAP for time series model, we'll have to come together again. Thank you so much. One more round of applause for Abhishek.
Thank you so much.